Hello everyone, thank you so much for joining us today. My name is Victoria Getz and I'm a Senior Marketing Coordinator at 2H Offshore. I want to welcome you all to our webinar today entitled Keys to Developing a Robust Life Extension Program for Flexible Risers. Before we get started, I'd just like to cover a few important housekeeping items. Firstly, this webinar is being recorded and will be made available to you soon, so please look out for a link to that in your email. Secondly, if you have any technical or content-related questions today, please feel free to ask them at any time. You can use the Q&A box that is located on the right-hand side of your screen. At the end of the presentation, we will go through as many questions as we can, but if you have further questions, feel free to contact our speaker directly after the presentation. And with that, I'm very happy to introduce our speaker today, Gilles Gardner. Gilles is a technical manager at 2H Offshore in Aberdeen. Gilles has over 15 years design, analysis, and integrity management experience of flexible riser systems, including cross-section design, in-situ analysis, manufacturing, fatigue assessments, inspection, and life extension. He holds a Bachelor of Engineering degree in Mechanical Design and Manufacturing from Memorial University of Newfoundland. He is a chartered engineer and a member of the Institution of Mechanical Engineers. So now I will turn things over to Gilles to get us started.
Thank you, Victoria, for the warm introduction. I'm excited to be here today speaking to you on this topic and hope you will all find the information useful. Welcome you all from wherever you're joining us from. So just to start off, a brief outline of what I'm going to present today in the webinar. I'm going to start off by laying out some outcomes, what I'd like to accomplish today, give you some background both on flexible pipe and on life extension in general, and then go into a little bit more detail about flexible pipe itself, particularly the kind of the main focus that will have the biggest impact on doing life extension. A little bit more information to understand damage, degradation, and failure modes of flexible risers. What are the most common ones, and how they're going to impact the general life, and potentially the impact it would have on life extension. And then I'm going to go into a little bit more detail about the methodology itself. And today I'm going to focus predominantly on an analysis type of methodology for life extension. But I'm trying to incorporate as many things as possible, particularly how we, what kind of design data is important to have at our disposal, how we would conduct global and local analysis, and then really look into a little bit of detail in the areas of conservatism and how that could give us some benefit when we're looking at a life extension. Then I'm going to kind of cement it a little bit with a case study, talk about an actual project and how the life extension was approached, and wrap it up with some conclusions at the end. So this slide, this is what I'd like to be able to accomplish today. I talked about those failure modes. I'd like to give you some more background on those, what are the most common ones, and understand their impact. All of this is going to be backed up by an integrity management program, or it becomes part of an integrity management program. So I really want you to appreciate the benefits of having a good one in place, and then understand how that advanced analysis can help to provide a more accurate assessment of the remnant life of flexible risers. And then understand also, or learn how extra data, environmental, operational, inspection, monitoring data can help us in our goal to maximize the life of maximize the value of a life extension analysis. So a little bit more background, like I said, on flexibles and life extension in general. So I'm going to talk today about unbonded flexible pipe, and you'll understand in a couple of minutes why I'm using that term. And I'm going to use a fairly typical type, the most common type of flexible riser pipe. And I call them complex multi-layer structures, and they can be quite complicated, but this is a pretty pretty basic one. They're complex because we've got multiple materials, we've got shapes, different layers, and those layers are not bonded to one another. So I use the sports team analogy here. Every layer has a specific function, and quite importantly, those layers are free to move relative to one another. And this is really important for when we talk about hysteresis. And hysteresis in flexible pipes is caused by the friction loading on the tensile armor wire layers, and that's generated in response to bending and the contact pressures that occurs between each of the layers. So this affects risers that operate with high internal pressures or that are in deep water and that have large external pressures as a result, and or high tension loads. What this does is it modifies the bending stiffness quite significantly. With the wave loading cycle, the bending and unbending of the pipe, the stiffness behavior will change. So it goes from what we would expect to be a linear behavior to a non-linear behavior, and that has a big impact on predicting the remaining life, because we're effectively going to be calculating fatigue, and the bending stiffness has an impact on that. So two of the references that I'll use quite a bit through my presentation, through the webinar, are the API foundation documents, the specification for unbonded flexible pipe, and the recommended practice for flexible pipe. So why do we want to do this in the first place? The decision to conduct a life extension will be based on safety, operational, or economic factors. So it'll be based on changes to operation, things like the function, the service, if we're changing service of a particular riser, the condition or relocation if we're moving it to a slightly different location and the configuration has changed. It may be based on changes to design codes, although those are pretty rare. They're mature now and they haven't changed. They don't change significantly now. But also instances of damage or exceeding original design parameters. So best example of that is we're going beyond the original design life, hence the life extension and why we're talking about this today. So the flexible riser manufacturers use a fairly conservative fatigue analysis approach at the design stage, and this is laid out in the API documents. So it's an accepted method. It's considered to be conservative. So things like using regular wave analysis and a conservative environmental load set, using high internal pressures, conservative vessel heading, so that the heading of the vessel is pointed in a direction that you will get the worst combinations of waves and current. And sometimes the analysis will ignore the hysteretic response. It simplifies the analysis and gives us a conservative answer. So refining these conservative parameters and use of supplementing them with operational data can result in a fatigue life improvement of up to 10 times. So particularly handy for what we're talking about today, life extension, but also that operational stuff that I was talking about, operational planning, doing this ahead of time, and fitness for service if we're looking at changing the function. So getting into riser damage, degradation, and failure modes. Coming back to that sports team analogy, each layer has failure modes. They've got their specific function. So because there are different materials involved and they do different things, each of them will have threats, failure modes, however you want to term it. So a lot of these are highlighted at the design stage, and the design takes care of mitigating quite a few of those, but we still have to deal with some as they happen operationally, from aging, regular degradation that we expect to have happen. So on the right, your very classic integrity management cycle wheel, looking at engineering review, looking at the kind of information that we would need to be able to conduct a life extension program or have as a part of our integrity management structure. We're going to use a risk-based approach to assess the threats, the failure modes that I'm going to talk about in the subsequent slides. And as much as they've been mitigated at design, we're still going to have to deal with them operationally. So develop an inspection and monitoring strategy early in our operational cycle to make sure that we're doing the kinds of inspections that will help us to highlight if there's been damage or degradation. Deploy those, implement them in operation, and not just let them tick over. Have it be an active process, so we can confirm and refine that the frequency that we're doing those inspections is giving us the kind of information that we need, and we're incorporating that the data that we're gathering and the experience from operation into our integrity management cycle. So going into a typical cross section, and I'll explain on the last slide of this section. But this is a fairly typical riser, and regardless of water depth and pressure, these components make up a fairly typical riser. So I'm going to start from the outside in, and we start. Our first layer is the external sheath. It's a polymer sheath, so it's a little bit more susceptible to things like holes, tears, ruptures, cracks. It sees lots of high external pressures in deep water risers, but in the top sides it also sees things like UV from being in the sun, or wear and abrasion from being in contact with the interfaces at the FPSO. It also comes in contact with ancillary components, clamps, buoyancy modules, arches, and then at the touchdown point, it's quite an active area, coming in contact with the seabed. So there's potential for, or higher potential for, damage to occur. So ultimately, it's the failure mode or the threat involved in this layer is a breach. We don't want that to happen, because we will then have a flood of seawater into the space where we house our carbon steel components, which is referred to as the annulus. That's the space between the outer and the pressure sheath. If that gets flooded with seawater, we're going to reduce our service life. The carbon steel layers in the annulus have no protection, and will their life will be significantly reduced, obviously, from corrosion happening. Even though we do have some cathodic protection, we don't want to depend on that to extend the life of our riser. We want to make sure that we keep that outer sheath intact. So sometimes we use strategies at design like multiple outer sheaths in order to mitigate high friction areas, touchdown points, or other areas where we potentially have a breach. Our next layer, our first kind of structural component made of carbon steel, is our tensile armors, and they provide our tensile capacity. They're laid in pairs, cross-wound, helically wound flat wires that give the pipe its tensile capacity, and we want to keep those wires healthy. So not only do we want to keep them dry, we want to keep them organized. There's a lot of redundancy in the wires, but we want to keep them organized and together. So we don't want any of those wires to rupture, disorganized, become bird caged or cluster, and that can happen when the pipe goes into compression. Generally, flexible risers like to be in tension, and that helps us to avoid any disorganization of wires. And then one of our threats is if we do have an outer sheath breach, corrosion is going to significantly reduce the capacity by corrosion of our tensile armors. So our next layer, which is another steel layer, is our pressure armor, and the pressure armor is quite a specialist layer, and it gives the hoop capacity to our pressure sheath. So a pressure sheath being a polymer sheath, this is a steel backup to that, and it gives us that strength, so we know we can go at much higher pressures than the polymer layer could do on its own. Once again, we want to keep that layer dry. We don't want the wires to rupture or to break. We want them to be organized. It's an interlocking layer, helically wound, so we want those to stay, to that locking mechanism to stay intact, because we don't want that hoop capacity to be reduced, and that can be reduced through collapse or ovalization. And obviously we don't want things like cracks happening. If that that layer was to become flooded with seawater, corrosion is going to be a significant degradation mechanism. Our next layer is our pressure sheath. Now this is our, it's kind of, you could say, is our kind of key layer. It's our pressure retaining layer. So it is supported by the layers around it. So obviously, it's quite key to keeping our bore fluid in its place, and it's being a polymer layer, it's susceptible to this, to similar failure modes that we've talked about previously, looking at holes or cracks, rupture, blistering. We don't want any of that to happen, so we want this layer to stay very healthy. One of the things that we do at design is in material selection, this layer needs to be very inert, so it's not going to react with any of our production chemistry, any of our injected chemicals. The temperatures that it's going to operate at are going to be within its capabilities, so it's not weakened by pressure, by temperature. And we don't want things like high pressure to have an impact on creating micro cracks that can lead to significant cracking. We also don't want, because this is a layer that's going to withstand some significant amount of pressure, we don't want creep to occur. So creep is a very slow flow of the polymer that gets squeezed into the spaces of the adjoining layer, so into the spaces in the pressure armor. So we don't want that to happen, and we make sure that we have the layer is thick enough that we don't have any significant damage that is going to occur to our pressure sheath in the case of that flow over time. And also, we don't want it to age prematurely, so I talked about being compatible with their chemistry, making sure that nothing that we're going to do is going to have an impact on that. Carcass, our last layer, it's in our process fluid stream, but it's not a fluid retaining layer, and this provides our collapse resistance for our pressure sheath. So it's a helically wound shaped layer. It's our only semi-exotic steel layer, generally stainless steel. So we don't want things like holes, crevices, pitting, or thinning. We want that layer to stay organized. We don't want it to become unlocked. We don't want it to collapse or ovalize and weaken that layer, and then subsequently take away the collapse resistance of our riser. So we're looking at issues again, because it's a helically wound layer, circumferential cracks. We don't want issues from wear and fatigue, particularly from things like pigging. It would be, other than the process stream, it would be the only other thing that would come in contact. Not all flexibles are pigged, but if they need to be pigged, we just need to make sure that the materials that we're going to choose for our pig to do that job are going to be compatible with the material that we have in our carcass. So I breezed over a couple of layers. You might have noticed in between the tensile layers and the pressure armor, there's some polymer layers there. They're simply there to reduce friction, because we have a riser, a dynamic riser, or we're going to assume that it's a dynamic riser. It's going to bend, and the tension is going to change. Those layers are there to stop fretting, friction between the steel components, so they don't prematurely age. Now, I mentioned that this is a rough bore pipe. There's also smooth bore risers. They're not as common, and so I guess the extra, the carcass would be absent. The extra thing to highlight here would be that they would be much more susceptible to collapse. So installation conditions and tensioning conditions during installation are very important. They're generally installed flooded to give them some extra support from a fluid, and their pressure, their internal pressure is quite important as well. That requires to be required to be full of fluid, or at least have the pressure in order to withstand the threat from collapse. So the other layers need to be doing a little bit more of the collapse resistance job, but not as common as this application. So how do we approach the analysis type of life extension methodology? So we're looking at gathering as much data as we can. Obviously, if we're in operation many years into operations, sometimes getting a hold of the design data is difficult. Documents disappear. So gathering that information, but also gathering information about current uh, environment. The vessel has anything changed? Is the internal fluid changed from design? What are the operating conditions like now? Can we benefit from any kind of monitoring? And obviously, inspection data, visual inspection, other tests that have been done during the operational phase. Can we gather all of that in this gather phase, and then decide what type of analysis is going to benefit us? If we know that regular wave analysis was done at design, can we benefit from things like irregular wave analysis in whichever domain that we choose? Will be a benefit to us to reduce some conservatism. So we put all that information together, develop a load case matrix, or basically these are combinations of loads and the occurrences that would represent how the system is going to behave going forward, and potentially predicting how much life has been taken out of it. So possibly using what was done at design, but updating that to properly simulate the environment, and identifying what the base matrix looks like, and possibly if we have key concerns, identifying sensitivity cases that we could that we should be looking at in further detail. And then the final step is post-processing this global model data. So this model is going to represent the system, all of the system components. So all of the risers, the ancillary devices, the floater, or whatever the riser is connected to. And what we're looking at is obviously going to be focused on fatigue. So identifying what areas the fatigue is occurring, and not just accepting the same locations that was taken at design. Things may have evolved and changed. So looking at the analysis based on the new data in order to confirm those locations, and then extract things like combinations of either tension and angle or tension and curvature as ranges, as histograms, or even as detailed as a time trace in order to go to our next step. So the kinds of software that we would use to do a global analysis, I've talked a little bit about that, but being able to model the system as a whole, and including all the components. So not just looking at the riser in isolation, but looking at how the riser interacts with the interfaces, bending stiffeners, bell mouths, eye tubes, things like that. Where sliding contact may also be an issue, so that needs to be properly captured in order for us to quantify the types of stress that the riser is going to see, in order for us to assess how much life has been taken out of the system so far, and then be able to predict how much remaining life is left. So then moving into a little bit more detail, we go from the global to the local. The global, we look at the riser as a pretty much a homogeneous pipe. So we start to break that down a little bit more into the individual layers and components of the pipe. So we transpose those local results in those key areas into the loading for the global analysis, and we then start to look at the reaction, or the response of the system, starting to take more details into account. So things like the friction in between each layer, the pressures in between the individual layers, the key layers, in order for us to calculate the armor wire stresses. And those will give us an ability to calculate the fatigue. We apply then, after we've calculated stress and calculated fatigue, we apply the SN curve. So the curve that gives us the amount of damage that is going to occur with combinations of curvature and tension, or stress and number of cycles. Apply a fatigue safety factor, and which is prescribed by the recommended practice and specifications, which is 10 times the service life. because risers are generally in high-risk areas. So they're near where humans are. They're transporting hydrocarbons, and they're generally high pressure. So the impacts to safety of humans and safety of the environment is important. So a generous safety factor is applied in order for us to calculate our remnant life. A little bit more detail about how the local analysis is done. It's going in and doing a detailed modeling of the cross section. So each of the layers are modeled with the primary focus being on the carbon steel components, because they're the layers that are most prone to fatigue. It is possible that the other layers will be the limiting factor, but generally it is the steel components. We're going to model the transitions in more detail. So things like I mentioned it before, bend stiffeners, bell mouse. That transition response is really important. And here is where we're going to start to look at the hysteresis effect. So that plot in the left-hand corner is the plot of how the bending stiffness changes based on the combinations of bending and tension. And we're going to do this in an iterative approach, and I'll talk about this on the next slide. So this is how the overall workflow looks. The global response calculation is done, modeling the system as a whole, with the pipe being modeled in a homogeneous way, and then into a little bit more detail modeling. The local model being created and the hysteresis loop is incorporated. So those first three circles are a bit of an iterative process. So we use the local model to calculate the hysteresis response. Then we feed that back into the global response and make sure that that's been captured. So then we get our an appropriate combination of tension and curvature. That allows us to calculate the stress in those carbon steel components, the layer stress calculation. We apply that SN curve, apply that safety factor, and are able to calculate remnant life. So starting to look at areas of conservatism. So I mentioned this one before, and just a visual representation of how we can use irregular wave analysis. So regular wave, like I mentioned, is a very accepted method of applying the waves in our model, but it's conservative because every single wave has the same amplitude. The periods are identical. The periods are identical, and the plot on the right shows you a difference between the wave and how it not how it impacts, but what the wave looks like. And is much more, the irregular wave is much more representative of what happens in real life. So it starts to bring back that conservatism. It still represents the amount of energy that the riser would see in those conditions, in the predicted conditions. And we can also take measured conditions and generate irregular wave traces in order to calculate the damage that's been accrued. And I think what's important to note here is that the regular wave method, even though it reduces conservatism, it complies with the approach that's laid out in API 17b. It is much more accessible than it was before. Computing power nowadays means that we can do this type of analysis without really taxing our computers. And running lots of different load cases. So it allows us to introduce these reductions in conservatism. Another area is looking at those critical locations and how those critical fatigue locations that we identified in our global, that we look into more detail in our local, how we can calculate those stresses and how we can also see that the bending is not always happening in one plane. So instead of using that as a conservative approach that might have been done at design, we can see how the bending and tension can be applied in up to 16 locations around the pipe circumference. So we can use the irregular wave stress response, look at how the individual components like the tension and the curvature can be combined, and how they don't all happen in the same part of the same location around the circumference of the riser, and how they come together to create stress. So instead of stacking them one on top of another, we're looking at how much stress occurs from the individual components. Another area of conservatism is the application or the use of wave spreading. So instead of assuming that those regular waves are hitting the pipe in the same direction, same location, they will have different energies as they are impacting the circumference of the pipe. So not only using irregular wave analysis, but using wave spreading, we've seen that applying wave spreading has reduced or has increased the life of the tensile armors by a factor of 2, and for pressure armor wires up to a factor of 3. Another area of conservatism is internal pressure. So instead of assuming that we have a high internal pressure, we see that as we get higher and higher pressure, the response, the damage increase is exponential. So having accurate internal pressures is essential. So not just taking one pressure and applying it to the whole of the riser, but also looking at what's actually occurring. So taking operating pressures. So we see that exponential effect in the plot on the right, but on the left we see that we've got different stress effects at different pressures, obviously as we're going up, increasing in stress as a result of that internal pressure. And then taking that one step further, taking into account the variations along the catenary. So we know that tension, internal and external pressure are going to change, especially for deep water riser. External pressure is going to vary quite significantly from the top to the bottom, but the internal pressure as well, for the same reasons that the fluid column will have an impact on the pressures at the top versus the bottom. And so the hysteretic response at those locations can be modeled, included in the model, and we've seen that has a significant impact on the calculation of damage and fatigue, and we can effectively break the riser down through the catenary length in order to sum the damage that's occurring at the different levels. So how do we wrap this all up in a real example? So I'll lay out a case study that occurred on an actual project. Really, so the decision had kind of been imposed in a sense to do a life extension or to calculate the remnant life, and the objective was to determine whether the risers could continue service, calculate the fatigue usage to date, and see what was left. And this was driven by the fact that from design, things had moved on quite significantly, and some of it not intentionally. So the headings of the vessel were predicted to be quite benign, and in really quite good headings when it came to the impact of fatigue. And it turns out that those headings were not occurring in the same frequency that was predicted. Also, the internal pressures were different than what was predicted at design, so that had an impact on fatigue. The REO information, or the response amplitude operators of how the vessel behaves to waves and current, had been refined and was more onerous to the system. And then, sort of to counteract that or to balance that out, replacing the regular wave analysis that had been done at design with irregular wave in order to get a more representative response, including time series in the local analysis, in order to calculate the damage that had occurred. So this plot really just to kind of show the outcome of it, the application, once all those other inputs had been updated, moving from a regular to an irregular wave analysis showed that a significant improvement in fatigue life by a factor of 2 to 3 on the tensile armors, and quite a significant factor between 10 and 15 times for the pressure armor wires. So, sort of wrapping up now, coming back to the learning outcomes, I I hope that I've been able to help you to discover the most common failure modes of flexible risers. Each of those have to be examined when you're looking at your own particular case, but these are the most common ones, and understand the impacts that they can have. Appreciate obviously the benefits of having a risk integrity management program. There should be one in place, and see how having one is going to bring obvious benefits. And then hopefully you could see that there's definite benefits from conducting an advanced analysis, or using advanced techniques that to help to provide a more accurate assessment of the remnant life for flexible risers. And then how gathering data, environmental, operational, inspection, monitoring data, can help as a contributing factor to maximizing the value of a life extension analysis. So just to conclude, really important, if I didn't emphasize it enough, that you have an integrity management system that's employed, that if you take the decision to do a life extension program, that it's really important to revisit the original design life assessment, and challenge the assumptions, not to be argumentative, but just look at them and see where there's opportunities to reduce conservatism, and then incorporate as much as you can measured events, recorded pressures, recorded temperatures, vessel behaviors, and then really understand what the threats to the system can be. Are they event-based? Are they condition-based? Is it time, degradation, those kind of things? And there's great documents that are out there that really bring together the experience of the industry, and lay out some really good recommended methods for undertaking a life extension program. So you really have to seek to take the opportunities to reduce conservatism, do them in a measured manner, because you're realizing that you're starting to scale things back from the well-established conservative approach that would have been taken at design in order to determine the remnant life. And hopefully all of this results in a way for you to justify to yourselves as an operator, or to others, perhaps some outside influences, or outside things like governing bodies, in order to justify extending the life of your system. So that's the end of my presentation. I'm sure that there's quite a few questions that have come in, so I look forward to answering them, and I hope you've enjoyed my presentation.
Thank you, Gilles. We do already have some great questions from our audience, so I will go ahead and get started asking those. So the first question: which component is most fatigue critical and sensitive? What is the main cause of fatigue failure?
Okay, well, I would say that because I talked about a standard riser, and there isn't such a thing, but the most common riser configuration is the one I laid out today. The tensile armor wires, I would say, are the ones that see the ones that perhaps are the perception that they're the ones that are most fatigued. When you think about what they go through in a dynamic riser, so in critical areas where they're near the top, near the hang-off of a say a deep water riser, they will be the ones that will see the most work. So they're going to be bent, they're going to be in high tension all the time because they're at the top. So they're supporting the weight of the riser. So that combination of tension and bending will contribute to the biggest input for fatigue. But if you compare that to, say, a riser in a different service where you see big variations in pressure, then it's possibly your pressure armor that will see, if the tension isn't as high, but you have big variations in pressure, the pressure armor will see the most fatigue because of those variations. So they will be bent or stressed in a different way because of those variations in pressure. So really it does focus, if you had to lump it into one component, it's your armors. So they may be your tensile armors, they may be your pressure armors, but it's your armors, and they're the ones that for fatigue is your biggest focus.
Okay, the next question, what has been the general historic experience of wear on the outer layers in the touchdown region where the riser contacts the seabed, and how is this affecting riser lifespan?
Okay, so once again, every situation is unique. If you have a touchdown area that's sand or clay, you generally don't have big issues because the polymer that's chosen is very robust, so it can withstand quite a bit of friction. It's not, and it's generally a touchdown. It's not sliding. It's basically, impact, light impact, depending on the configuration. So it tends to be areas where you have a mixture of sand and rocks, or if you don't have sand at all, rocks at that. But then that's an opportunity at design for that risk or that failure mode to be mitigated. So designing the system with that external sheath, or even going further and using an ancillary device like riser protection. So that's extra polymer, very thick extra polymer layers that are installed in half shells around the outside of the riser at that particular location, knowing that your riser is going to be bashing up and down on the seabed onto sharp rocks or other deposits that are going to cause issues. So those are probably the most common applications. So it's really comes back to that understanding how the system is behaving at design, or catching it after, if it's not caught at design and it occurs in operation because there were other factors that we completely didn't understand. Those can be installed retrospectively and help to protect the riser. The threat is that if you breach that outer sheath, that you're then going to flood the annulus, and if you flood the annulus, unless it's taken into account at design, you will significantly shorten the lifespan of your risers, because then you've flooded the area of the pipe that has carbon steel components, and their life will be reduced as a result. So it's about keeping that outer sheath healthy through an extra outer sheath or through an ancillary device that will help to protect that.
Okay, thank you. Another question, is it possible to instrument and measure the loads on FR so uncertainties for global analysis can be minimized?
Yes, there has been various different methods used. Using strain gauges is very difficult because accessing those carbon steel components, that needs to be thought of well in advance, and they tend to be a little bit on the delicate side. So my understanding is applications of that has had limited success. More successful has been things like fiber optics embedded into the edges of the carbon steel components in order to gather that kind of information. But then again, they are a bit on the delicate side, and the history behind them has been that there has been limited valuable information gathered from it. In other words, the period that they were able to monitor was rather short. Another area that you might not have thought of originally would be there has been some validation testing sort of in the area of validating local analysis software, where they've instrumented sections of flexible pipe, and they've done that in a controlled manner. So it's out of the water in a laboratory environment, but they were able to bend the flexible component, put tension on it, and then start to measure that response. So that has probably been the biggest source of valuable information as an input to fatigue, and calibrating and validating the finite element modeling that we do for remnant life assessments and calculating fatigue.
Okay, thanks, Jill. Another question. Have 2H had experience with flexible life extension when 10 times FOS is not achieved in fatigue? And if so, what was the process for quantifying the risk for acceptance by the operator or regulatory body?
Yeah, that kind of two separate things. So yes, there's always the potential for doing a life extension program that the answer is not going to be positive. That the accepting the fact that there's still a very conservative application of a safety factor that's applied at the end of it, that is very difficult to challenge unless the riser's in an area where the service is very low risk, or there's very low impact. If there was a rupture to the environment or to safety of people, that would really be a very specific application, and would be about the only time that you could reduce that. So it's difficult to challenge it, and ultimately the acceptance of that has to be not only the operator, but perhaps a governing body or a regulatory body that would accept that. I would say our experience would be that it wouldn't be accepted. So taking the decision to continue to operate would generally not be done, because you're continuing to operate taking on quite significant risk. So I think the only thing that I could offer in addition to that would be, then we would look at ways to reduce stress, or reduce continued fatigue consumption by doing things like reducing pressure. So if you can demonstrate through the analysis that operating at a third of the original operating pressure gives you a low fatigue consumption going forward, if you have life left, it's the only way that you can continue, or you can justify to continue to operate with the same configuration. Otherwise, you're looking at recommending replacing the riser segment to be able to continue to produce.
Okay, I think we have time for one more question. So this one says, the enhanced fatigue life relies on accurate armor stress predictions from nonlinear FEA. How are these complex FE models validated?
Good question. So I touched on it just a couple questions ago. So the local analysis software is validated through mechanical testing. So I'm not talking about individual components, but the system as a whole. So having a segment of a representative segment of a flexible and instrumenting it, looking at the stresses in the pressure armors and the tensile armors, measuring those through different cycles, so internal pressure, tension, and bending, and that's the validation process that's used both at a flexible vendor level and an independent level. 2H has not been involved in that directly, but that type of requirement for validation is part of the document that I mentioned during the webinar. The Annex G of API 17b goes into the details of the requirements for the software to be validated, and it must be validated through direct physical testing.
Okay, well, thank you so much. That's all the time we have for today, but as we mentioned earlier, if we didn't get to your question, or if you would like to continue this discussion, please contact Gilles directly using the details provided here. Thank you to our audience for your time and participation. We hope you all found this useful and will join us for more webinars later this year, covering a range of riser and subsea topics. Again, please look out for the recording of the webinar in your email in the next 24 hours, and we hope you all enjoy the rest of your day. Thank you.